All right, so the ideas in this video continue off from the ideas about matrix multiplication. So when we multiply real numbers, in multiplication of real numbers, we have the idea of an identity, a multiplicative identity. In other words, there's a real number, where if you multiply it by any other real number, you get that real number as a result. What do I mean by this? I mean, there is a real number, which we'll call it, say, A. Okay, where if you multiply A by any B, you get B. Anyone know what that A is? Well, it's 1, right? It's because 1 times X is equal to X, and also in the other way is also true. X times 1 is X. So we call 1 the multiplicative identity, or just the identity for real numbers, multiplication of real numbers. So is there an analogous thing? Is there an analogous idea in matrices? So is there a special matrix where if I multiply it by any matrix A, I'll get A as a result? So the answer is yes, and we call this the identity matrix. So here it is. So the truth is, there's not one identity. There isn't one identity matrix. There are many identity matrices, and it depends on the order of the matrix that we're dealing with. So let n be a natural number, any natural number. So an identity matrix we'll call it I sub n, is an n by n matrix. So notice it's a square matrix. The number of rows is n, and the number of columns is n. So it has the same number of rows as columns. And we'll call this matrix A, where A sub ij is equal to the following. So it's equal to 1 if I is equal to j, and it's equal to 0 if I is not equal to j. So for example, I sub 3 would be the following matrix. So it's going to be a 3 by 3 matrix. And now we're going to fill it in with ones and zeros. So we put in a 1 if I is equal to j. So here the row is 1, the column is 1. So I is equal to j, so we put a 1. Here the row and columns are not the same, so we put a 0, and we put a 0 here. Then a 0 here again. Here it's row 2, column 2, so we put a 1, and then a 0, and then 0, 0, 1. So notice it's a matrix where the diagonal here from top left to bottom right is 1s, and the rest is 0. So that is the identity matrix that's a 3 by 3 identity matrix. Of course, what would I sub 4 be? So that would be a 4 by 4 matrix, 1, 1, 1, 1, with the rest all filled in with zeros. Okay, so this would all, that's the idea. Now, why do we care about identity matrices? So as I was saying earlier, they actually act as an identity for multiplication. So let me just state that fact. So fact, if A is an n by n matrix, it could be any n, it could be any matrix, n by n matrix, then A times I sub n. So in other words, this matrix, which could be any matrix, any square matrix, n by n matrix, multiplied by the identity matrix of size n, n by n, is going to be equal to just A, and equivalently will be equal to I sub n times A. So in other words, here is a case where the order of multiplication doesn't matter. So this is going to be equal to this, and they're both going to be equal to just A itself. Let's do an example. So let's say we have this a 3 by 3 matrix like this: 1, 2, 5, 6, 7, -2, 3, negative 3, 0. And I multiply by the identity matrix. And here, since we're dealing with a 3 by 3 matrix, I'm going to multiply it by the 3 by 3 identity matrix. By the way, when we write the identity matrix, sometimes we don't write the subscript n in cases where it's obvious that in cases where it's obvious what the order is, we just write I and don't bother writing the subscript n. So let's see. So we have 1, 0, 0, 0, 1, 0, 0, 0, 1. So that is the identity matrix. And if we do the multiplication, okay, I'm not going to bore you with the steps, but try it out, do it on your own, and you'll see that you come out with 1, 2, 5, 6, 7, negative 2, 3, negative 3, 0. Okay, what do we see here? A times I is equal to A. So in other words, this matrix is the identity. And it also works in the other order, in the opposite order. So if I do the identity times A, we'll get A as well. Okay, and you can verify that. All right, so that's the idea of the identity matrix. Now we have a related idea of matrix inverse. So let's look at the analogy for real numbers. So for real numbers, given any real number, given a real number like well, almost any real number. So given, let's say, a real number like, I don't know, 3, okay? There is another real number where if I multiply it by 3, I get the identity, right? Remember, 1 is the identity for real number multiplication. And there is another real number here that I could provide, which when I multiply by 3 will give me 1. We call this other number the inverse of 3. Okay. More formally, it's the multiplicative inverse because it's the inverse for multiplication. But anyways, what is that number? Well, for here, it's 1/3, right? 3 times 1/3 is 1. So given any real number, I guess except for 0, well, I guess the inverse for 0 would just be 0, maybe, not sure. But no, it wouldn't be. I'm sorry. It wouldn't be 0. So for 0, this wouldn't work, right? 0 times what is equal to 1? Well, not possible, right? So it wouldn't work for 0. So, but for any other real number except for 0, it has an inverse. And, anyway, so that is the idea for real numbers. So is there a similar idea for matrices? So that's what we're going to talk about here. So we're going to see that just like with real numbers, sometimes the inverse exists and sometimes the inverse does not exist. So for almost every real number, there is an inverse. But for one specific real number, for 0, there is no inverse. Okay, so we'll see that also for matrices, sometimes yes, sometimes no. So first, let's do this. So here we have the matrix 1, 2, negative 3, and 5. And if I multiply it by the following matrix, so it's going to look pretty strange: 5/11, negative 2/11, 3/11, and 1/11. Okay, and the result is 1, 0, 0, 1. In other words, the result is the identity matrix. So what do we see here? We have a matrix A times another matrix B. Whoops, and this equals the identity matrix. So we call B the inverse of A, and we write it as this, A inverse. Okay, the similar similar notation to the inverse function. Remember we talked about the inverse of F. So here we're dealing with matrices, but so this is the inverse of A. Why is it the inverse of A? Because when I take B and I multiply it by A, I get I. And it also works, and this also works in the other order as well. So what I mean is, if I do B times A, it's gonna give me the identity as well. So 5/11, -2/11, 3/11, and 1/11 multiplied by 1, 2, -3, 5 is also equal to the identity matrix. Okay, so that's why B is the inverse of A. In other words, B is considered the inverse of A because A times B is equal to the identity, and B times A is equal to the identity. So that's why B is the inverse of A. Now, B doesn't always exist. So given a matrix A, it's not always possible to find an inverse of A. All right, but so we'll give the rule for that in a little bit. But first, let me just state the definition of inverse, matrix inverse. So let A be an n by n matrix. So first of all, this, as you this idea of matrix inverse only applies to square matrices, to n by n matrices. So so if it's a let's say a 4x3 matrix, not going to have an inverse. But if we have a square matrix n by n, then there might be an inverse. Even here, not always is there. So here we'll say this: if there exists an n by n matrix B such that A times B is equal to the identity matrix, and that's also equal to B times A, then B is the inverse of A. And can be denoted as A inverse. So B is A inverse. Okay, now the general problem of finding the inverse of a matrix is beyond the scope of this course. Okay, you can take a course in linear algebra, and you know these are all this is beyond the scope of the course. But we're going to do a very specific case. So we're going to deal specifically with the case of a 2x2 matrix. So given any 2x2 matrix, we're going to state how to find the matrix if it exists. First of all, how to determine whether the matrix exists, and then how to find a matrix if it does exist. But again, we're only going to deal with 2x2 matrices here. If you look in the book, there's a later chapter which talks in more general terms about the inverse of a matrix. But it's not a straightforward topic, so we are not going to do it. And in general, we don't need to know it for this. We don't really actually need to do it in this course. So, but if you're interested in learning more, take a linear algebra course. So we are doing. We want to find the inverse of a 2x2 matrix. But first, before we do that, I want to introduce a new idea, and that is a determinant. So the determinant, and we're only introducing this because it's part of finding the inverse. So the determinant of a 2x2 matrix. Okay, so let's say we have a matrix A, which contains some elements. We'll call them A, B, C, and D. The point is they could be any numbers. A, B, C, and D could be any numbers. Okay, then the determinant of A, which we write like this, det of A, determinant of A is equal to AD minus BC. Okay, that's it. So for example, so let's say we have A is equal to 1, 2, -3, and 5. Then the determinant of A is going to be, so it's going to be A times D, so it's going to be top left times the bottom right minus the top right times the bottom left, which is 11. Okay, another example. Let's say we have A, which is this matrix, 1, 2, 2, 4. Okay, then the determinant of A is going to be, so again, 1 times 4 minus 2 times 2, which is 0. Okay, now you might say, what's the determinant of a larger matrix, like a 3 by 3 matrix? Well, you can look in the book, later chapter discusses it, or take a course in linear algebra, but we don't care about that. We're just talking about 2 by 2 matrices right now. And so the determinant of a 2 by 2 matrix is this. Okay, so now we can talk about how to find the inverse of a 2 by 2 matrix. So again, there's a general problem of finding the inverse of a matrix, but we're not dealing with that general problem. We are just talking about a specific case where it's a 2 by 2. So finding the inverse of a 2 by 2 matrix. So let A be a 2 by 2 matrix. So it has elements A, B, C, and D. Okay, there could be any numbers. If the determinant of A, okay, we just talked about that. If the determinant of this matrix A is not equal to 0, then the inverse of A is equal to the following. 1 divided by the determinant of A times the matrix D negative B negative C A. Now, how in the world we got this formula? Well, it's not, you can actually figure it out on your own if you really think about it. And yeah, but doesn't matter. We don't need to understand it. Okay, so this is the formula. So what we're going to do is I will show an example in a minute. But let's just say, what if, so this is all if the determinant of A is not equal to 0. But if the determinant of A is equal to 0, then the inverse doesn't exist. A inverse doesn't exist. Okay, so do an example. So if well, let's say let's say we have A is this matrix 1, 2, -3, 5. Okay, so what is A inverse? So the inverse of A is going to be the determinant of A times let's just move this down and drop. Okay, so now we already know the determinant of this matrix. We found it before. It is 11. So we're going to do 1 divided by 11. Right, that's so 11 is the determinant as we found earlier, multiplied by, so D, so that's 5 times let's see, negative B, so that would be -2 times negative C, so that's -3, so that's +3, and then A, which is 1. Okay, and then we have to simplify this. So this is not matrix multiplication, it's just scalar multiplication. Right? We're taking a number and multiplying it by a matrix. So that's easier. So that's 5/11, and then -2/11, and 3/11, and 1/11. Okay, so this is the inverse of A. So in other words, A times A inverse is going to be equal to A inverse times A, which is going to be equal to the identity matrix. All right, that's the last video of the semester. Wow.